Hello everyone, this is continuation of our last lecture on electrostatics where we discussed about electric dipole, electric flux and Gauss law. So let's start from where we stopped in last class. So Gauss law. So Gauss law basically says that the net flux through any closed surface, net flux due to any charge or any continuous or discrete charge through any closed surface is given by 1 by epsilon naught times the charge enclosed by that surface, right? So let's say the for assumption this surface is a spherical cell, right? And we have a charge, this is a closed surface, and we have a charge called plus q, which is present inside the spherical cell, and this surface is S, right? So now the net flux, the total flux which is going outside this particular surface is what? Charge enclosed, which is plus q divided by epsilon naught, right? So for uh, vacuum this is epsilon naught, for other medium it will change to epsilon, which is given by what? Relative permittivity into epsilon naught, right? Okay. So what exactly? So by definition we know flux is what? Flux is nothing but the dot product of electric field intensity and area, right? Means the product of field component along the area vector into the area. Okay. So let's say this we have a small area delta S, right? So delta phi will be what? E into delta S, right? So this net flux is what? This summation of all this delta phi, right? This is summation of all small areas if I cut across, right? So this is a continuous body. So it will be what? Integration of what? Delta phi, right? So integration of what? E ds, right? So when it is evaluated along a closed surface, we call it as surface integral, right? So expression for Gauss law is basically the closed integral of electric field component along the area is given by charge enclosed by epsilon naught, which is basically flux is given by net charge enclosed by epsilon naught, right? Okay. So let's solve a very small problem on electric flux on Gauss law. So let's say there are two spherical cells, right? Which encloses charge plus q here and plus 2q here, right? And this is S1 and S2. So what is flux through cell S1 and what is flux through cell S2? This is the question. So I can simply apply Gauss law here. What exactly is net charge enclosed by S1? You can say that net charge which is enclosed by S1 is only plus q, right? So I can simply say that the net flux through S1 is what? Plus q by epsilon naught, right? But what about S2? S2 you can see S2 is enclosing plus q as well. S2 is enclosing plus 2q as well. So net charge enclosed by S2 is plus 3q, right? So flux which is coming out of S2 has contributions from this plus 2q also and plus q also. So net flux through S2 will be what? Plus q plus 2q by epsilon naught, which is plus 3q by epsilon naught, right? Okay. Okay. Let me change this question a bit. Uh, let me change the charges here. So let's say this has something like plus q and we have a minus q here, right? And we have plus 2q here, right? So these are the charges. So now for S1, what is the net flux? You can say that again for S1 the charge enclosed by S1 is plus q only. So net flux through S1 will be what? Plus q by epsilon naught, right? What about S2? S2 is again enclosing what? Plus q by epsilon naught, which is plus 2q by epsilon naught, right? So what exactly is these two extra charges? Plus 2q and minus 2q plus 2q and minus q. What exactly are these two charges? So according to Gauss law, it basically takes into account only those charges which are present inside the surface of interest, right? So the closed surface of interest S1 and S2 is not enclosing minus q and plus 2q. Hence we have nothing to do with these two charges, right? Okay. But what happens if I take one more sphere, right? Let's say I take one more sphere here and name this as S3. Okay. So now tell me what exactly is flux through S3. So now what is the amount of charge S3 is enclosing? It is plus 2q plus q plus q minus q. Hence it is plus 3q. So phi through S3, it will be nothing but plus 3q by epsilon naught. Right? Okay. Very clear? So now, as I said, this is only applicable when all the mediums are vacuum. Let's say if I put a dielectric inside this S1, which has a relative permittivity of epsilon r, so net flux through S1 will be what now? Plus q by epsilon r epsilon naught. Right? Okay. So we just discussed the application of the problem on Gauss law. So now Gauss law is nothing but it is an extension from Coulomb's law. Yesterday we derived Gauss law from Coulomb's law. How? We took a point charge here plus q. We draw a Gaussian surface and we derived that how the flux net flux through this surface will be q by epsilon naught, right? So it is nothing but a extension of Coulomb's law. So why we use Gauss law? What benefit do it give? So that we will learn in the applications of Gauss law, right? So the topic is applications of Gauss law. Applications of Gauss law. So Gauss law helps us to calculate flux crossing any closed surface using a very simple expression where you can choose a symmetrical surface and simplify your calculation. So using Gauss law, I can actually calculate flux and hence field for a lot of charged bodies easily, which would take me some time by calculating using analytical and integration methods, right? Let's start with one, right? Let's start with one. Electric field due to long straight charge conductor, right? Conductor. Okay. So this can be a wire, this can be anything. So long means I'm assuming that the length of this conductor is very high. It is very high than the point where I am calculating the field. Okay. So since this is a linear body, right, charge is distributed along the length. What is my concerned electric density here? That is linear charge density, right? I explained yesterday, lambda is nothing but, linear charge density is nothing but charge per unit length, charge by length. Okay. So this long straight conductor would look something like this. This is a long straight conductor. It has charges on it distributed along its length. Okay. So now at a point P from this at a distance R, I need to calculate the electric field, right? What exactly is electric field due to this long straight conductor at point P? So analytically we can say that the direction of electric field would be something in this direction. Let's say the electric field is EP, it will be something in this direction. Why? Because all the charges will be contributing from all parts to this particular field, right? And you can see the net component of field will be in horizontal direction because the vertical direction will field will cancel out each other, right? So the net direction will be in this direction. But what is the magnitude of this electric field intensity at point P is our interest, right? Okay. So let's draw a Gaussian surface for this. So this is infinite rod. So I'm not very bothered about what is the exact length, but I'm bothered about the length which is placed inside my Gaussian surface. So Gaussian surface for this particular conductor will be what? This will be a cylinder, right? Because cylinder is the symmetry for this particular conductor. So let me draw a cylinder. Not very great at drawing. Maybe you can draw properly in your notebook. So this cylinder is Gaussian surface for this conductor, right? Let's assume that the length of this is L. Our radius obviously is R, right? So now net flux due to this conductor uh, for this closed cylindrical surface will be what? It will be given by again Gauss law, which is charge enclosed by epsilon naught, right? So before going to that, now let's see that how many surfaces this cylinder has, right? You see, this is S1, right? This is S2, and this is S3. So three surfaces and hence three area vectors. The direction of area vector is outward, outside the surface, not inside. So three surfaces and three area vectors. So now you can see that S1 and S2 is perpendicular to the direction of electric field. So there won't be any flux contribution to them by this conductor, right? You can see that this is perpendicular to electric field, this is perpendicular to electric field. You know the flux is what? Es cos theta, cos 90 is 0, so there is no contribution. So S3 is only interest for me, right? And this is what I'm calculating, the field at point P, right? So now, before calculating that, what is the net charge? So lambda is the linear charge density of this conductor, right? Lambda is the linear charge density of this conductor. So and length is L for this Gaussian surface. So since lambda is net charge by length, I just wrote. So lambda is nothing but Q by L. So Q is what? Lambda into L. So net charge enclosed by this Gaussian surface is what? Lambda into L, right? So now, what is the expression for Gauss law? Expression for Gauss law is closed integral of E ds is given by charge enclosed by epsilon naught, right? So electric field is obviously at point P will be constant because of this, since it is not a varying field and this is a long uniform body. Integration of surface ds will be what? The net surface area of this cylinder. What is the net surface area of a cylinder? You know, curved surface area of a cylinder. This is, since I'm calculating for this surface, this is what? 2 pi r L, right? And Q enclosed is nothing but this charge, right? So it is lambda L by epsilon naught, right? L will cancel out each other. So EP is what? Lambda by 2 pi epsilon naught r. So this is expression of electric field because of a long straight conductor at a point P which is situated at a distance r from it, right? This conductor has charge linearly distributed along its surface, along its length, right? So this is the expression of electric field due to this long straight conductor, and we derived this using Gauss law, right? Okay. So we just discussed electric field due to a long straight conductor, infinitely long, and how can we derive it using Gauss law. So next application for Gauss law is electric field due to non-conducting infinite sheet, right? So sheet basically means, let's say we have a sheet area. Sheet is something, let's say this can be a sheet which has charge, but this is non-conducting, right? So it won't be transferring its charge. The charge will reside on this particular surface where I inject it. So this is the sheet of interest for me. So what is electric field due to this non-conducting infinite sheet? Again, the length of this sheet can be infinite. The thickness is negligible, right? So let me draw a sheet. So this is like a sheet. This has a charge on its surface, right? And at a distance, again, at a distance, let's say r or something from this sheet at point P, I need to calculate my electric field. Okay, so let's again take a small part of this infinitely long sheet and make a Gaussian surface, right? Right, okay, so this is the Gaussian surface. So before doing that, again, this is a sheet. The charge is distributing along the area. So my concerned charge density is sigma, which is surface charge density, which is charged by area, right? Okay, so this is my concern, charge density. Okay, so what is the net charge? Net charge enclosed by this Gaussian surface. Let's say S is this area, right? S is this area which I am covering. All three are S along this horizontal line. So this S, like it is cut in this way. So what is the net charge enclosed by this cylindrical surface? The net charge will be what? It, it is S into what? Sigma, right? So this is what it is, right? So now again for this Gaussian surface, how many area vectors we have outwards? S1, let's say S1, this is S2, and this is S3. My electric field is along this direction, right? So now you can say S3 this time is perpendicular to this electric field. So this field will not contribute to any flux in S3, right? So only area of interest is S1 and S2, right? So again applying Gauss law. Gauss law says net integration of electric field over area is given by charge enclosed by epsilon naught, right? So here I can say that flux through S3 is 0, right? But what about flux through S1 and S2? Because since this point is P, there will be an equivalent point P here as well, P dash. And this, since this is a conducting, sorry, this is an infinite non-conducting sheet, this will have field in both the direction, right? So this will have field in, this will emit electric fields in both the directions, right? So net flux will be this into this field into this, and this field into this surface. So I assume that this surface is S and S like this, right? So net flux due to through S1 will be what? Flux through S1 will be ES cos 0, which is ES, because they both are parallel, not anti-parallel. Again S2, it will be again phi S, right? Because electric field direction is away from positive, so towards both sides it will be away from positive and away from positive, right? So now net flux is what? Phi S1 plus phi S2 plus phi S3, which is nothing but ES plus 0 plus ES, which is 2ES, right? Now I can put it here. Net flux is charge enclosed by epsilon naught. 2ES is nothing but charge enclosed is this sigma into S by epsilon naught. So electric field is SS will cancel out each other, sigma by 2 epsilon naught. So this is the expression of electric field due to non-conducting infinite sheet at any point P away from it. You can observe that this is no longer dependent on this distance R. So whatever distance we place it, the field is constant. The value is sigma by 2 epsilon naught. It is dependent only on the charge density of the sheet, right? Obviously epsilon naught is constant for a particular medium. So we just discussed electric field due to a thin, infinite, long sheet, non-conducting sheet, and how it is independent of the independent from the distance at which we are calculating it. Now, next topic is electric field due to spherical cell. Electric field due to spherical cell, right? Let's say this is a hollow spherical cell. Hollow spherical cell basically means that the charge is distributed on the area of the spherical cell, and it is not embedded inside. Embedded it's empty, there is no charge, but surface is carrying the charge, and hence my concerned charge density is again sigma, which is charge by area, surface charge density, right? Okay, so let me draw a diagram. So let's say this is a spherical cell, right? It has a radius capital R. Now I need to calculate electric field due to this spherical cell. So let's say at a point P at a distance R, I am calculating the electrical field intensity, right? So for that I need to draw Gaussian surface, which will be again a spherical shape Gaussian surface, right? So now there are three cases to it, right? This R can be outside this spherical cell. So, which means this R is greater than the capital R. This R means this point P can be at the surface of this spherical cell, which basically means R is equal to R. And this point P can be inside the spherical cell, which means the R is less than R, right? So let's discuss all these one by one, right? So let's say case 1, R is greater than R, right? Which what we have drawn. So Gauss law gives a simple calculation of how can we calculate electric field at point P. So net charge, what is the net charge enclosed by this Gaussian surface? You can say net charge is sigma into area. What is the area of this sphere? What is the area of sphere, you know? So net charge, let's say Q is the net charge, is nothing but sigma into area is what? 4 pi r square, right? So sigma into 4 pi r square, right? So what Gauss law states? Gauss law states that the net charge is given by charge enclosed, sorry, net flux is given by charge enclosed by epsilon naught, right? So now E is constant, obviously this will come out, right? What is this particular ds? ds is the integration of total area, which is the total area, which is nothing but 4 pi r square, right? And let's say this charge enclosed is nothing but q and by epsilon naught. So what is the electric field here? Q by 4 pi r square epsilon naught, right? If I rearrange it, it looks like 1 by 4 pi epsilon naught q by r square, right? Okay. Yeah, so one thing which we did wrong here is the net charge is nothing, not small r, this will be capital R, because charge is only till the circumference, right? So this will be capital R square. So this is the expression of electric field at a distance r from the spherical cell, hollow spherical cell. So now you can see this is equivalent to electric field due to a point charge. Let's say if I keep a point charge at the center of the sphere and I calculate the field at point P, this will be exactly even with this particular expression, which is 1 by 4 pi epsilon naught q by r square, right? Okay. And we can write this in terms of sigma as well. What it would turn if I write in terms of sigma? This will be 1 by 4 pi epsilon naught, right? Q will turn to sigma into 4 pi r square, and this will be again r square. 4 pi will cancel each other. Sigma r square by epsilon naught r square. Something like this it will come up, right? Okay. Okay. So now let's say this r is equal to r. Okay. So case 2. Case 2. R is equal to R. Okay. Now what happens? How this diagram will change? So this is my point P now, right? And this circumference itself is my Gaussian surface, right? So again, the charge enclosed will be what? Sigma into area, which is 4 pi r square, right? This time r is equal to r. So net flux is what? E 4 pi. Net area is r square. It is charge enclosed by epsilon naught. So this is what? E equal to q by 4 pi r square epsilon naught, which is same as E equal to 4 pi r square epsilon naught, right? So this is again similar as we calculated, just this is now r is replaced by capital R, since this is the point of interest is at the circumference, right? So for case 2, when r is equal to r, the expression is given by this. Now I can again replace q from here to this and place it here. Can you do it yourself? This will become sigma by epsilon naught, the field, right? The field becomes a constant value independent of the distance now, right? Since we are calculating at the circumference and radius is a constant here, right? Let's discuss the third case. where case 3 is r is less than r, right? Now what happens? How this diagram will change? Let me redraw it for you. So now point P is somewhere inside this spherical cell, right? So let's say this is my point P. It is at point R, and this is my Gaussian surface, right? This is my Gaussian surface. So now what is the electric field at point P, right? I just explained in the beginning that this is a hollow sphere and it has charges only at the surface of it, right? So what is the charges enclosed by this Gaussian surface? You can say it is zero, right? The charge enclosed is zero in this case, since this is a hollow case and there is no charges inside. So you can simply say the electric field inside will be zero, since charge enclosed will be zero, right? The expression itself said that this becomes zero and area into E into S will be zero, and hence E equal to zero. So electric field inside it will be zero, right? So if I bring all three here and try to write it, so for, let's say this was my diagram R, and R is my point of interest. So case where R is greater than R, case where R equal to R and R less than R, electric fields will be like, it is zero here, it is Q by 4 pi epsilon naught R square here, it is Q by 4 pi epsilon naught R square here, right? So this is the electric field for hollow sphere, right? So next application is electric field due to a solid sphere. So solid spheres will have particles inside it as well. It will be a tightly packed sphere. It will have charges embedded along its volume and not surface. So every volume you pick from it, it will have significant charge. So exercise for you is you need to calculate the electric field due to solid conducting sphere for all three cases, and then we will discuss it tomorrow in the next session, right? And we will stop here for today. Thanks.